this right here. So good morning, everybody. And so today we're talking about polynomial functions. And actually it says today polynomial functions, but that'll be this week polynomial functions, and we'll finish that up mostly all today. It's possible we'll start rational functions by the end of the week, but we will finish polynomial functions for sure this week. And there's a little outline of the things that we're going to talk about. I'll discuss that in a minute. Something to bring up for everybody is the homework extension. I want to make sure everybody saw that I extended the due dates on the homework from sections 4.1 and 5.1. I gave you an extra week to do that. And so that's due on the 11th, and so that's due on Wednesday of this week at midnight, by the end of the day on Wednesday. So be taking care of that homework on 4.1 and 5.1. Also note that the homework for 5.2, 5.3, and 5.4 is due the following week, I guess that would be Tuesday of the following week. So pay attention to those due dates and try to keep up with your WebAssign homework. And please ask me questions on WebAssign homework during lecture or during office hours, or sending me an email, and we'll definitely go over it. As far as your exam 1 grade status, so exam 1s, I got most of those last Wednesday, so I am working on them, and I'm about halfway through your class right now, and I anticipate finishing the exam 1 grades, or finishing grading them today. And so what I will do is, after I've got them graded, I'll email everybody, but I'm going to post on your WebAssign grade book. You have a grade book that's available to you on WebAssign. It's where you see your homework grades and all that kind of stuff. And so I will post that on your WebAssign grade book, I would say right now by tomorrow. So that would be by Tuesday, and that would be the October the 10th. So sometime during the day tomorrow, I'll post those on WebAssign. I will email everybody that I've posted them on WebAssign. And then if you want to get your graded exam back so that you can see the marks on your test and how it was graded and everything, then what I will ask you to do, and I'll mention this in the email that I send everybody tomorrow, is I will ask you to email me, and if you email me, then I will just simply respond to your email and attach the electronic copy of your test to that with it graded. So that's kind of the process we'll use during the semester. So I should have them posted tomorrow, so hopefully I'll finish them today, get them posted tomorrow, and then I'll be ready to email them out to people during the week this week. So just email me, and I will send it back to you as an attachment. Okay, so that's how we're going to handle exams during the semester. All right, and your exam 2 is not for another 3 weeks, I believe, is when the window, 2.5 weeks now, I guess, is when the window opens up. And so that's something we'll start gradually talking about next week, and start headed towards, posting the review for that and all that kind of stuff. So, all right, so today we're talking about polynomial functions, and so I'm going to go back and maybe do a little bit of reviewing as we go through this, and then we've got quite a bit of things to talk about in class. So I'm in section 5.3 right now, which we started last time, and I want to finish this section up, and today for sure, finish section 5.4 for sure, and then start in section 5.5. All right, so if you recall, for polynomial functions, this is kind of where we are right now. Good morning, Dominique.
Good morning.
So this is where we are with polynomial functions right now. We have talked about how to find the degree of a polynomial function. We've talked about what the leading coefficient, and I abbreviate that LC, And we've talked about how to use those things together to talk about the end behavior of a polynomial function, right? So those are kind of the three things. We've also discussed a few other little items here, and then we're going to kind of start piecing this big puzzle together. And that's the way to look at this: is it's a big puzzle, and we've got all these pieces that we're trying to put together. And you'll start seeing gradually today and on Wednesday how these pieces kind of fit together. But so far, this is some other things that we've talked about, is that if you have a degree n polynomial, so if its degree is n, whatever that is, second, third, fourth, fifth, whatever, some things that we've discussed. First of all, the polynomial has n zeros automatically. The number of zeros and the degree of the polynomial is always the same. Now, some of these may be zeros of multiplicity. And so, remember, we did talk about that last week. So some of these may be zeros of multiplicity. And remember that a zero of multiplicity is a zero that occurs more than one time. So a zero that happens more than once. Sometimes what you'll see on videos, if you're watching videos from other sources online, they'll refer to those as repeated roots. Sometimes they'll call them double roots. By the way, the word root, when you see the word root, you're talking about zeros in a polynomial. So roots and zeros are kind of the same thing in some ways. So they're in some contexts they're interchangeable words here. They're not completely interchangeable words, but they kind of sort of mean the same thing. So zeros of multiplicity are zeros that occur more than one time. And we're going to talk about how that relates to the graph today. Something else we've talked about with degree n polynomials, not only does it have exactly n zeros, but it has at most n minus 1 turning points. And we've talked about that last week also. And we'll start looking at that again on the graph today. So has exactly n zeros. Some of them may be repeated zeros. Has at most n minus 1 turning points, which means it's always one less than the degree of the polynomial. All right, also remember that zeros, and we did talk about this last time also, zeros come in three flavors, three different kinds of zeros. You have rational zeros, and rational zeros are like 2/3 and -5/4 and 6 and 0 and -1, right? Those are all examples of rational zeros. You also can get irrational zeros. So irrational zeros are ones typically that have radicals. So like 1 plus or minus the square root of 2, or 3 plus or minus the square root of 5 over 6, or just plus or minus the square root of 8, let's say square root of 10. Things like that. With a radical in them, those are all examples of irrational zeros. In both cases, those give you x-intercepts. So if you have a rational zero, you have an x-intercept. If you have an irrational zero, you have an x-intercept. You have places where the graph crosses the x-axis. And then there's a third type of zero, and the third type of zero is an imaginary zero. And imaginary zeros are ones with i's in them. So like 3 plus or minus 6i, or just plus or minus 7i. Could have fractions in it, that doesn't matter. 1 plus or minus 3i over 5. Those are all examples of imaginary zeros. So this is actually going to come up for us during these next couple of sections, is what kinds of zeros you've got when you're looking at a graph. And also remember that imaginary zeros, no x-intercepts there. Right? There's no place on the graph for an imaginary zero. Not on, because we're only graphing real numbers. We're graphing in what's called the real plane, and so there's no place for imaginary numbers in this. They don't show up in the real plane like that. All right. So now some things that we've talked about, and then this is going to kind of push the envelope a little bit from where we were last week. So what we want to do is look at some examples, and I'm on page 390 in your book, and this is section 5.3, homework, and I want to look at some problems and start talking about how various things relate to graphs, things like that. All right, so this is problem 42, and I'm going to be kind of skipping around on this page for a little bit because there's a couple of different things I want to talk about, but they're not in the order I typically deal with them. So in problem 42, we have f of x is x plus 3 squared times x minus 2. All right, so that's a polynomial function that's in factored form. So this is a polynomial function. And in particular, it's in factored form. So in other words, it's already written out as linear factors. That is a really good form for us because it's going to make our lives easier as we work through a problem like this. All right, so some things that I would ask you to do on a polynomial function like this is I'd ask you to write down the degree of the function. And this is stuff we were talking about last week. Now, the degree of this factor, since it's squared, is degree 2. This is a degree 2 factor. This is a degree 1 factor right here, and so you add those together because remember, you're pretending that what would happen if I multiplied all this stuff out, what would be the biggest power in x that I'd end up getting, and I'd end up getting an x cubed in there somewhere. And so this is a degree 3 polynomial, and remember that's odd, which is important for us, that it's an odd degree polynomial. The leading coefficient, all the x's have 1's in front of them. And so when you multiply all this out and you got that x cubed, it's going to be a 1x cubed. So the leading coefficient's a positive 1. And then the end behavior. All right, so it's an odd degree function. So remember, with the end behavior, you think about the cube function. You know, and the cube function kind of looks like this. And so odd degree polynomials have end behavior that looks like the cube function, either the cube function or the cube function turned upside down. So the end behavior for this function, just like the cube function, is going to be a graph that looks like this, falling to the left and rising to the right, like that. That would be our end behavior. And so you can draw out the end behavior like I just did, or you can use the notation we introduced last week. And we could say that as x goes to negative infinity, in other words, as x goes to the left, that y, or f of x, also goes to negative infinity. And as x goes to positive infinity, and remember that means we're going off to the right, then f of x, in this case, is rising, and so f of x or y would go to positive infinity. So I want you to be able to write it out either way, either drawing the picture or writing out those symbols like that. All right, so degree, leading coefficient, and end behavior are always things I'm going to ask you.
I had a question about finding the degree and leading coefficient.
Okay.
So when finding the leading coefficient, like once we multiply, like and factor all that stuff out, wouldn't there be like a 3x in there somewhere? Like making the leading coefficient 3?
Yeah, but what's the coefficient of the x cubed term? So the question is, you know, Dominique was asking about what happens if you multiply all this out. And so let me show you, if you, and actually let me go to the next page. Actually, I can fit this in at the very bottom down here. So if you've got f of x equals x plus 3 squared times x minus 2, like that. So first of all, when you square out the x plus 3, remember that's x plus 3 times x plus 3, and you'd use the FOIL method to multiply it out, and you'd get x squared plus 6x plus 9 when you do that. And then that would be times x minus 2. And then you'd multiply that by taking the x and multiplying it through each of those terms, and do the same thing with the negative 2. So when you multiply all that, you'd end up with x cubed plus 6x squared plus 9x minus 2x squared minus 12x minus 18. And so when you're finished, you'd end up with x cubed plus 4x squared minus 3x minus 18. Now, we don't care about, for the end behavior, we don't care about any of the other terms except the first one. That's the term that controls the end behavior of the function, and it also controls the degree of the function. And so for the end behavior, that's the only term we care about. We don't look at the other terms at all. We just look at that x cubed term. So the x cubed term tells us the degree is 3. It also tells us the leading coefficient's positive, and then that gives us, those two things together give us the end behavior. Okay, Dominique, are you okay with that?
Yeah, I'm okay with that.
That makes sense?
And then about finding the degree, so we wouldn't be like adding the 3 plus the 2 plus like another 2 and a 1?
No, you would be just looking at the degree of each of the factors. So at the very top of your screen where I wrote x plus 3 squared and I wrote degree 2, notice at the bottom of the page there, notice that this is what I'm talking about, is that factor, right, when I say degree 2 at the top, I'm talking about that if you multiplied it out, you'd end up with an x squared in there.
Yeah.
Right? Okay? And then the other factor is degree 1. That's this factor down here, the x minus 2. And then when you've got it factored like that, all you're doing is adding the degrees together. So if you have factors, you're just adding the degrees of each of the individual factors together. So I add 2 and 1 and I get 3. You know, if you had, let me write another polynomial down here. If you had f of x is x plus 5 cubed times 2x minus 1 squared times 3x plus 7, like that. So what's the degree of the first factor? The degree of the first factor is 3. Yeah, if you cube that factor, if you multiplied x plus 5 times x plus 5 times x plus 5, you'd end up with an x cubed. The degree of this factor is 2, because you square it and you're going to get an x squared. And then finally, the degree of the last factor is a 1, because it's just an x to the first power. And so the degree of the polynomial, you add those together. So that'd be 3 plus 2 plus 1, or a 6th degree polynomial.
Okay. All right, that makes a lot more sense, because I was getting it wrong on the homework.
Okay. Yeah, and that's very important, so that's good that you asked that. So, all right, let's see. We've got the degree, the leading coefficient, the end behavior. The next thing I would ask you to write down here are the zeros for the function. And so the zeros, remember, you set y equal to 0, and you have this equation, but all that means is you're just setting each factor equal to 0 and solving, and you end up with x equals -3 and x equals 2. Now, an important thing to talk about here is notice that when you have a linear factor, so x plus 3 is a linear factor and x minus 2 is a linear factor, that when you have a linear factor for a polynomial, that you get a 0. That linear factors and zeros go together. So when you have a linear factor for a polynomial, you get a 0 for the polynomial. When you get a 0 for the polynomial, you have a linear factor. Notice I put a double-ended arrow between those two things. And that's an important relationship for us when we're talking about polynomial functions, is that linear factors and zeros go hand in hand. Those are together. Okay? So that's something that's going to come up repeatedly for us. So linear, and this is sometimes, by the way, called the factor theorem. Factor theorem says that if you have a linear factor, then you're going to get a 0. And if you have a 0, you're going to get a linear factor. Right? And you actually might see it written this way sometimes, that if x minus k is the linear factor, where k is just some constant, then that means that k is a 0. Right? That's sometimes called the factor theorem, And it's just telling you that linear factors and zeros go together. Okay, so what do I have in my problem? I have negative 3 is a 0. Now notice x plus 3 is squared. And so that means that negative 3 is a 0 of multiplicity 2. And so what I'll ask you to do is I'll ask you to write down negative 3 as a 0, and then right next to it, I'll just have you abbreviate multiplicity 2, which means that it's a factor twice, or it's a repeated 0. And then 2 is also a 0. So notice how many zeros we ended up with. This is a third-degree polynomial, and sure enough, we ended up with 3 zeros. Remember, I told you on the last screen that the number of zeros and the degree of the polynomial is always the same. And in this case, we get 3 zeros. Negative 3 is a 0 twice, and then 2 is a 0 also. Now, we'll talk about how that relates to the graph in a minute. And now the x-intercepts, well, notice that these zeros are both rational zeros. And go back to the previous screen. Remember what I told you, that if you have rational or irrational zeros, you get an x-intercept. Okay? So these are also x-intercepts. You have negative 3 0 is an x-intercept, and 2 0 is an x-intercept, like that. The y-intercept, remember how you find the y-intercept is you set x equals 0. In other words, you're looking at f of 0 in our function. And so f of 0 in our function would be 0 plus 3 squared times 0 minus 2. And so that would give me 9 times negative 2, or negative 18. And so my y-intercept's at 0, negative 18, like that. All right, so these are the things that, so far, that I'm going to ask you about a polynomial function, any polynomial function. Is I'm going to ask you the degree, I'm going to ask you the leading coefficient and behavior, the zeros for the function, whether the zeros are zeros of multiplicity or not, ask you for the x-intercepts and the y-intercept. In fact, on exam 2, you'll see some polynomial functions, and there'll literally be a list, and it'll be kind of like fill in the blank. Degree, leading coefficient, and behavior, zeros, x-intercepts, y-intercept. Those are the things I'm going to be asking you to write down. All right, now let's, before we look at any other examples, let's look a little bit at the multiplicity of a 0 and how that affects what the graph looks like. All right, so if you have, let's say you have a graph of a polynomial function, and it looks like that. That's at least part of it. That's how f of x looks. Notice it has an x-intercept at 2, 0. So you have an x-intercept at 2, 0. And so that means that this function has a 0 at x equals 2. And it also means that x minus 2, this is the factor theorem, x minus 2 is a factor of the polynomial. All right, and then the other thing to talk about is if you just look at that graph, just right around the graph, just right around the x-intercept. So if you could kind of zoom in a little bit, right? Just I'll just draw a little box around it. If you just look around like that, what you might say here that the graph kind of looks like a line. And when the graph kind of looks like a line, just right around that intercept, it's not a line, it's obviously a curve, but if you just zoomed in right around that intercept, the graph kind of looks like a line. What that tells you is that the 0 happens or occurs only one time, because it's like a linear factor like that. And so that means that you don't usually say multiplicity of 1, by the way. Multiplicity kind of implies that the 0 occurs more than one time. So what you're saying there is that it's probably just a 0 that occurs once, right? Now, if the graph kind of looks like this instead, let's see. Let's say you have a graph. who knows, it does something like this. Whoops, do a little bit better job here. It kind of looks like that, and that's the intercept I'm really interested in. Notice that this one has an x-intercept at 3, 0. And so that means we have a 0 at x equals 3, and that it means that x minus 3 is a factor of the polynomial. And also notice that if you look at the graph at that intercept right there, the graph kind of looks like a parabola. And remember, we get parabolas when we have second-degree polynomial functions. So the graph kind of looks like a parabola if you just zoomed in around that intercept right there. What that tells you is that you have a 0 of multiplicity 2. Right, you have a 0 of multiplicity 2. So when you have a graph that kind of looks like a parabola, then you're going to get a 0 of multiplicity 2. Those go hand in hand. Now, depending on the graph, it could be a 0 of multiplicity 4 or 6. It's probably going to be 2, and we'll talk a little bit about that more later. So if the graph kind of looks like a parabola. All right, now sometimes you'll get graphs that look like this. Let's say we have a graph, and this is what it looks like. Let's say we've got a graph that is coming up like this. It kind of looks like that. And it's not the greatest graph in the world, but... So notice that I've got two x-intercepts here. I've got an x-intercept at -2, 0. And so that means you have a 0 at x equals -2. And it means that x plus 2, x minus -2, or x plus 2 is a factor. X plus 2 is a factor. We also have that there's an x-intercept at 4, 0. And so that means that there's a 0 at x equals 4. And it means that x minus 4, remember, it's always x minus the 0. So since there's a 0 at -2, x minus -2 is x plus 2. Since there's a 0 at 4, it'd be x minus 4. X minus 4 is a factor. Now also notice that the graph at -2, the x-intercept there, the graph kind of looks like the cube function right around that intercept. If you zoomed in right here, it kind of looks like the cube function. And so that means that what we have here is that -2 is a 0 of multiplicity 3. So I'm going to add that in up there right above it. You have x plus 2 as a factor, but it's a factor of multiplicity 3, like that. Right? It's a graph that kind of looks like the cube function is going to give you a 0 of multiplicity 3. Now notice the other graph here, this at -4, that one kind of looks like a line when you look at that graph. And so in that one, you just get, you just have x minus 4, you just get that 4 is a 0 once. And you don't have a 0 of multiplicity there at all. So the multiplicity of the 0 is connected to the way the graph looks like at that x-intercept. Okay, so notice on the problem we just did a second ago, going back to this screen, we had a 0 of multiplicity 2. And so that tells us that at -3, this graph kind of looks like a parabola. All right. And so we're going to talk more about that in a second. In fact, let's talk about that now. Let's kind of put that together. This is problem number 50 in your book. It's on page 391. And on this problem, you're actually given a graph of a function, of a polynomial function. And you've got that this graph has an intercept at -1, an x-intercept at -1, has a y-intercept at 2, has a peak here at 1, 4, and then it has another x-intercept here at 2. And the graph kind of looks like this. It's kind of steep, comes in like this. And kind of looks like that. So notice this graph has 2 turning points, and it also has 2 x-intercepts. So, and the directions here, by the way, are to actually write down a formula for this particular function. All right? We can actually do this. We can actually write down the equation for this function. All right, so we have that -1 is an x-intercept. And so what does that tell us? That -1 is a 0. And it also tells us that x plus 1 is a factor. And because the graph kind of looks like a parabola, because of the shape of the graph at that intercept, shape of the graph kind of looks like a parabola, tells us that -1 is a 0 of multiplicity 2. Now again, technically it could be a 0 of multiplicity 4. We don't have enough information specifically at this point to say that, but you know, since it looks like a parabola, we're going to go ahead and use the least degree here. So the shape of the graph tells us that that -1 is a 0 of multiplicity 2, because it kind of looks like a parabola there. And so not only is x plus 1 a factor, but we know that x plus 1 squared is probably going to be a factor, is a factor. All right, so we have the -1's an x-intercept, and that told us that ends up giving us that x plus 1 squared has got to be a factor for this function, this polynomial. And then also, we have another x-intercept. We have the 2 is an x-intercept. And so this tells us that 2 is a 0. And it also tells us that x minus 2 is a factor. Because the graph kind of looks like a line, we say that 2 is probably going to be 0 only one time. So the shape of the graph, in this case, tells us that 2 is a 0 only one time. All right, so what does our polynomial look like at this point then? Remember, we're trying to build the polynomial. So the polynomial would have x plus 2 squared as a factor. I'm sorry, not x plus 2 squared, sorry. X plus 1 squared, that's better. And then also x minus 2 would be a factor as well. Now there could be, what we don't know about this function at this point, there could be a coefficient in front of there that's some constant, a. That wouldn't affect those zeros at all if it's a constant factor. And we actually do have enough information to tell us what that a value is. Because notice we've got that 0, 2 is a y-intercept. It's a place where the graph crosses the y-axis. And we can find a, so we use this to find a. Notice that 0, 2 is on the graph. So that means that f of 0, if you put 0 in for x, which would give us this equation, when every place I see a 0, or every place I see an x, I put a 0, But what do I know the answer's got to be? Because 0, 2 is the point, I know that the answer's got to be 2. And so this actually allows us to find A. You get A is 1, or I'm sorry, you get that A times 1 times negative 2 has got to be equal to 2. And that gives us that negative 2A has got to be 2, or that A has got to be negative 1. And so we've built the polynomial. The polynomial would be f of x equals negative 1 times x plus 1 squared times x minus 2. Right? So we've actually built the polynomial from the graph using the intercepts like that. And now, technically, there could be polynomials of bigger degree that fit the same graph, the same information. So that's why you'll see in the directions, they'll say find the degree, the polynomial of least degree that fits the information that you've got. All right, so that sounds good. Let's look at another problem like that one and see if we can kind of piece together the same kind of the same kind of information. All right, so this is problem number 54, a more complicated graph. So the graph on 54, I'm just going to write down the key points here. See, have an x-intercept at negative 4, another one at negative 2, a y-intercept up here at 3, another intercept here at 3 like that. And the graph kind of looks like this. This is the graph of our function f. All right, so we ought to be able to build the function from that information. So what do we have for the x-intercepts? Let's just go from left to right. We have an x-intercept at negative 4. And so this tells us that negative 4 is a 0. It also tells us that x plus 4 is a factor. And because the graph looks like a line, we can say that x plus 4 only occurs as a factor once, is a factor just once. Right? Because it kind of looks like a line right there. The same thing goes for the next intercept. You have the x-intercept at negative 2. That tells us that negative 2 is a 0. Tells us that x plus 2 is a factor for the polynomial. And because, again, it only looks like a line. Now, it's slanted in a different direction, but the graph kind of looks like a line right there. We say that x plus 2 is a factor once. Finally, the last intercept. We have an x-intercept at 3. So that tells us that 3 is a 0 for this polynomial. And so that tells us that x minus 3 is a factor. X minus 3 has got to be the factor. Remember, it's always x minus the 0. But this graph kind of looks like a parabola at 3. And so x minus 3 squared is the factor in this case. It's got to be a 0 of multiplicity 2. Right? So it's a 0, well, I'll put it right here, of multiplicity 2 because the graph kind of looks like a parabola. All right, so let's build our polynomial. So first of all, f of x equals, now there could be a constant in front, so we write down a. And then we have that x plus 4 has got to be a factor. X plus 2 has got to be a factor. And x minus 3 squared has got to be the factor. All right, and then we find the a value by using the y-intercept. The y-intercept is at 0, 3. And so that tells us that f of 0, right, if we're plugging 0 in for x, has got to be equal to a times 0 plus 4 times 0 plus 2 times 0 minus 3 squared, right? And we could just go through and calculate that, that would be a times 4 times 2 times 9. So f of 0 has got to be equal to 72a. But what do I know f of 0 is really equal to? I know it's got to be equal to 3. And so a has got to be 3 divided by 72. Just divide both sides by 72. Or 1 over 24. And so my function, when all said and done here, my function, f of x, is going to be 1/24 times x plus 4 times x plus 2 times x minus 3 squared. Right, that 1/24 is the constant in front for this particular function. And that would be the function of least degree that matches that graph. All right, so I would definitely, on the next exam, give you a graph like this, and or like these right here, and ask you to write down the equation from the graph like that. All right.
Will there always be like that constant a in front of the equation? Like we always have to solve for that?
Yes. Now sometimes, depending on the problem, Dominique, sometimes the a could be equal to 1, in which case it doesn't really show up because the a value is just equal to 1. It depends on the problem. And what we're going to do is we're going to look at using the y-intercept to actually find what that a value is. And sometimes we'll find that it's actually just equal to 1. That's just, it just depends on the problem. And remember, this is the polynomial of least degree. There could be other polynomials that fit the same graph that have a bigger degree than this one. We're finding the one with the smallest degree when we do this. So yeah, so I would ask you to find the a value also. Because remember, the a value since it's a constant, it doesn't give you any zeros. The only way you get a zero is if you have a variable in the factor. So since that's just a constant factor, it doesn't affect what the zeros are at all. All right, so I think probably wouldn't be a bad idea to write down a third example. And in fact, this one I think I'm just going to make up my own graph. And so we'll look at this one and see what how this graph gives us an equation. So let's say we have a graph, and all right, so I'm kind of thinking about how this is going to look. So this graph looks like this one right here. All right, now another thing that's a little bit of a difference on this problem is I'm going to say that this scale is by tens. And so that's 10 right there. That would be -10 right there. And so every tick mark on the y-axis is worth 10. So notice the y-intercept in this graph is at the point 0, 20. Right, that's our y-intercept. All right, so following along with what we were just talking about, excuse me, we see that -3 is an x-intercept. And so that tells us that -3 is a 0. Tells us that x plus 3 is a factor. And then, because of the shape of the graph, not only do we see that x plus 3 is a factor, but we see that x, it looks like the cube function right there, right? The graph, if you zoom in right here, kind of looks like the cube function. And because it kind of looks like the cube function, this is x plus 3 is a factor, and -3 is a 0 of multiplicity 3. And so x plus 3 is a factor, but what's the factor here is x plus 3 cubed is the factor. Like that. All right, we also get here that 2 is a 0, that x equals 2 is an x-intercept. And so you get that 2 is a 0. This graph kind of reminds you of the square function when you zoom in, right? That kind of looks like the square function. And so that kind of looks like a parabola. And so what do we get? That 2 is a 0 of multiplicity 2. And so we get that x minus 2 is a factor. And because it's a 0 of multiplicity 2, we get that x minus 2 squared is the factor. All right, and so what you get here is you get f of x equals, and then Dominique, you just asked about this in the last problem. There's maybe a constant factor sitting in front of this function that we have to figure out. And then we also know that x plus 3 cubed is a factor, and we also get that x minus 2 squared is a factor, like that. And so this is the polynomial of least degree that would fit this graph. The a value, we use the fact that 0, 20 is the y-intercept. And so what do we get here? The f of 0 is a times 0 plus 3 cubed times 0 minus 2 squared. So f of 0 would be a times 9, whoa, not 9, definitely not, times 27 times 4. And so you get that f of 0, 4 times 27 is 108, so you have 108a. But what do we know here? We know that f of 0 not only is 108a, but we know the intercept is at 20. So we know it's got to be equal to 20. And so you get that a is 20 over 108. So let's see. So that would give you 5 over 27. And so the a value is 5 over 27. And so our function finally is 5 over 27 times x plus 3 squared times x plus 3 cubed, times x minus 2 squared. Like that. And that would be our function. All right, so that's good information. That's stuff that we definitely need to know. Now, if the polynomial, all right, so we're kind of connecting factors and zeros and multiplicities and kind of looking at the graph around those x-intercepts. So the next question is, what if the function that you're dealing with, so this is still on page 390, this is problem number 14. This function that we're given in this problem is not factored. So you have f of x is x cubed plus 6x squared minus 7x. So now the first couple of things we can write down very easily from this problem that we've been talking about. The degree of this function is easy. The degree is 3. It's not in factored form, so you're just looking at the term with the biggest exponent. The leading coefficient is positive 1 because you have a positive 1x cubed. And so the end behavior for this function, it kind of looks like the cube function, and so the graph is falling to the left and rising to the right like that. Very similar to a problem we did a second ago. So that stuff is easy to do, but the zeros in this problem are a little bit more of a problem because this is not in factored form. So to find the zeros here, to find the zeros, factor the polynomial. Now, this polynomial is factorable, easily factorable using methods from intermediate algebra or introductory algebra because there's a GCF of x, first of all. So you can take that x out. And then x squared plus 6x minus 7 is an easy trinomial to factor, and it factors x plus 7 times x minus 1. So even though this polynomial was not factored, you could easily put it in factored form. And then from the factors, it's easy to find the zeros, right? The zeros, remember, you're setting f of x equals 0. And so you get this equation. And so the zeros are going to be x is 0. By the way, notice x is 0, or x is a factor, rather. And so that's a 0. So 0 is a 0. And negative 7 is a 0 from x plus 7. And 1 is a 0 from x minus 1. Remember, the factors and the zeros go together. The x-intercepts, those are all rational zeros, so those are all intercepts. So this is 0, 0 is an x-intercept, negative 7 is an x-intercept, and 1, 0 is an x-intercept. Notice that all these factors are raised to the first power, so there's no zeros of multiplicity. So it means the graph kind of looks like a line as you go through each of those intercepts. The y-intercept, when you substitute 0 for x, you just get that f of 0 in this problem is 0. And so the y-intercept's at 0, 0 also. You could make a really rough sketch of this graph. You don't have enough information here to write down where the turning points are, but you do have the intercepts, and you do have that the graph kind of looks like a line at each of those intercepts, and you also have the end behavior of the graph. So with all that information, you could make an educated guess at this graph, and this is not really a guess in this case. You're piecing those things together, and you know the graph has to be rising, has to look like a line, like this, and then somewhere in here it turns and starts coming back down, looks like a line. It's got to turn again somewhere in there and come back through. And notice a graph that's shaped like that fits the end behavior that I drew out at the very beginning of the problem. Now, what I don't know is where those turning points are, and that's not something we're finding right now, so don't worry about that at this point. All right, so that function was not factored, but it was factorable, and it was pretty easily factorable. Okay, so let's look at another one like that. Let's look at problem number 20. So number 20, you have f of x equals x cubed minus 3x squared minus x plus 3. All right, so that function, again, the first couple of things are easy to find. The degree is easy. The degree is 3. The leading coefficient, easy, is positive 1. The end behavior, easy. That just looks like the cube function. So the graph is falling as you go to the left, and it's rising as you go to the right, like that. No big deal. But to find the zeros, you do have to factor this polynomial and use grouping, in this case, to do that. It's not in factored form, so we want to factor it. So in the first, remember how you do this. You group first two terms and the last two terms. In the first group, there's an x squared that's common, and that leaves you with x minus 3. In the second group, there's a negative 1 that's common, and that leaves you with an x minus 3. Remember, if you're going to use grouping, you've got to be left with the same factor in both of those groups. All right, so now you take out the x minus 3, and you're left with x squared minus 1. And then x minus 1, x squared minus 1 is the difference of two squares, and so that factors x plus 1 times x minus 1. And so that polynomial factored pretty easily, and you get that form like that. And so the zeros from that function, because it's in that factored form, right, you get this equation. And so the zeros are easy to write down. The zeros are going to be at x equals 3, and at negative 1, and at 1. I just write them down as a list. Those all occur only one time. There's no zeros of multiplicity in this problem. And then the x-intercepts, those would all be x-intercepts. And so you have 3 zeros in x-intercept, negative 1 0 is an x-intercept, 1 0 is an x-intercept. And the y-intercept, substitute 0 for x. So you're looking at f of 0, which in this problem, that's just 0 cubed minus 3 times 0 squared minus 0 plus 3. Notice you're just left with the constant, which is 3. So the y-intercept is 0, 3. And again, because the graph kind of looks like a line at each of the x-intercepts, because none of those are zeros of multiplicity, should be relatively easy to make a rough sketch of the graph from there. All right, so now the question is, if the function is not factored, what happens if it's not easily factored like these last two problems were? And so that's what we want to turn our attention to now, is how do you decide when you have a factor for a polynomial if it's not in factored form, right? And so what we want to do now is look at polynomial functions that are not factored and not easily factorable. What do you do? How do you find those factors? So in other words, what if you can't really use the methods from intermediate algebra to factor the polynomial? So how do you tell something is a factor? That's a question here. How do you tell when, and I'm going to put this in quotes, something is a factor? And so, just look at constants for a minute. Look at whole numbers. The question is 7 a factor of 28, for example? Is 7 a factor of 28? Easy question to answer. And the answer is obviously yes, but how would you tell somebody that 7 is a factor of 28? Well, how could you prove it to somebody? And the way you would prove it is you divide. You take 28 and you divide it by 7. So you'd use division to do this. And you'd get 28 divided by 7, and you get a whole number as an answer. You don't get a fraction as an answer at all. You get a whole number as an answer. So yes, 7 is a factor. On the other hand, is 9 a factor of 28? And so you use division there. What happens when you take 28 and divide it by 9? Well, 9 goes into 28 3 times. The problem is there's a remainder, and the remainder is 1. And so you get 3 and 1/9. And so here you get a remainder of 1. So you get a remainder of 1. So no, not a factor. So what happens? You got 0 as a remainder in the first division. 0 was the remainder here. In other words, you didn't have anything left at the end when you divided. And so it all has to do with division. This all has to do with division right here and what your remainder is. If 0 is a remainder, then you have a factor. If you get a remainder of something besides 0, then you don't have a factor. Right? And so that's a way that we can decide whether with polynomials exactly the same way. We can decide whether a particular polynomial is a factor of another one by using division. Now, so for example, so I'm on section 5.4 in your book, by the way. Whoops. Let's say that we've got this question right here. Is x minus 2 a factor of this polynomial, 4x cubed minus 3x squared minus 8x plus 4? Now notice that polynomial is not an easily factorable polynomial. It does not factor by grouping. It is not a trinomial. There's no difference of squares. There's no common factor. And so it's not an easily factorable polynomial. But we're still faced with this question, is x minus 2 a factor of that polynomial? So just like I saw on the previous page, if you divide this, So if I take our polynomial 4x cubed minus 3x squared minus 8x plus 4, and I literally divide it, I'm going to write it as a fraction, by x minus 2, what is the remainder when you do this? When you do this division, what is the remainder? If the remainder is 0, then it is a factor. If the remainder is not 0, if the remainder is not 0, then you don't get a factor. So let's look at this division. Now, one way you could divide this is you could use long division. That's one method for doing this. But the good news for the long division is really a pain to do. It's really a mess, and we'd really rather not have to do that if we can avoid it. But for this one kind of polynomial, if you have a polynomial, or this one kind of polynomial division, if you have a polynomial and you're dividing by something in the form x minus k like this, a shortcut for long division exists for this kind of division, and it's called synthetic division. So it's called synthetic division. And we can use synthetic division to make a decision about whether x minus 2 is a factor of this polynomial. Now, so I'm going to show you how to use synthetic division. Some of you either watching at home or those of you who are with me this morning may have already seen how to use synthetic division. I'm going to kind of assume you have not seen how to use synthetic division. All right, so the first thing you do with synthetic division, now look at my problem right here and look at the general form for synthetic division, where you're taking a polynomial and dividing it by the form x minus k. So in our problem here, what is k equal to? Well, notice it's x minus k. So it's x minus 2. K is 2 in this problem. And that's what I need to determine is what the k value is in the problem. And what you're going to do is you're going to write what you're dividing by. In this case, what you're dividing by synthetically, which in this case is 2. You're going to write that k value down. You can put a little half box around it. And then you're going to write the coefficients of the polynomial you're dividing by, or you're dividing into, rather. These are the coefficients of the numerator, right? And so, you've got 4x cubed minus 3x squared minus 8x plus 4. Notice I just wrote down the coefficients for that polynomial. So there's my 4, there's negative 3, there's negative 8, and there's the constant 4. So you write those right alongside the k value like that. And then you leave a space and draw a horizontal bar like that. And then you always take the first number, the 4, whatever that number is. In this case, it's a 4. You take it and you drop it below this line. So I pull the 4 down like this. And then what you're doing here is you are taking the 2, this number that you've got sitting over here, and you're multiplying. I know this looks confusing, but you'll get the hang of this pretty quickly. Let's see, let's use a different color here. Let's use blue. So you take 2 and you multiply it by that 4, and you write that in the next column. And then you add that column. So then you add the column like that. And then you take this number and you write it in the next column. And then you add the column. And then you take this number and you write it in the next column. And then you add again. All right, so what do? I bring that first 4 down below the bar, and then I multiply the 2 times the 4. And that gives me 8. And then what do I do there? I add, I add each column. So I add negative 3 and 8, and I get 5. And then I take that 2 and I multiply it by 5, and I get 10. And then I add the column, and I get 2. And then I take 2 times 2, and I get 4. And I add, and I get 8. All right, so you're always, you bring that first number down, and then it's multiply, add, multiply, add, multiply, add until you finish the chart like that. What happens here at the end, and we're going to look at several examples of that, so don't, you'll get some practice before we leave here. This constant that we have at the very end here, that number right there, I always kind of put a half box around that number also. That number is called the remainder. And the quotient is represented by these coefficients right here. These are the coefficients of the quotient. The polynomial we were starting with was a cube. We divided by a linear term, so our quotient is going to be a second degree, and it's going to be 4x squared plus 5x plus 2. And then I take the remainder, which is 8, and I write it over the divisor. The divisor was my x minus 2. And by the way, that 8 over x minus 2 on the previous page is exactly like this 1/9 from the 3 and 1/9 right there. The 1 was the remainder, the 9 was the divisor. So I'm doing exactly the same thing right here. 8 is the remainder, x minus 2 is the divisor. Because these are polynomials, we usually put a plus sign for that fraction. And then the answer to the question was, is x minus 2 a factor of this polynomial? And the answer is here, no. The remainder is not a 0, and because it's not a 0, we don't get a factor. Now that 8 does have some other meaning for us that we'll talk about on Wednesday, in Wednesday's lecture, but we're not going to do that today. So, all right, so that we got that was not a factor. And you should always, kind of check your arithmetic and make sure that you've done all the arithmetic correctly as you go through the problem. All right, let's look at problem number 39. This is the same kind of question. So we're trying to decide, we're using division and synthetic division to decide whether something is a factor. All right, so in problem number 39, you have is x minus 2 a factor of 3x to the 4th minus 6x cubed minus 5x plus 10. All right, so the k value in our problem is 2 because we're trying to decide whether x minus 2 is a factor. All right, and so we're going to divide synthetically by 2. We write down the polynomial. Now you have to be really careful when you write down a polynomial with synthetic division, in that all of the terms must be present. When I say all the terms, no powers can be skipped. And notice in this polynomial, an x squared gets skipped. And so when you write this out for synthetic division purposes, you have to think of the polynomial as 3x to the 4th minus 6x cubed plus 0x squared minus 5x plus 10. So notice that that placeholder has to occur inside the polynomial there because the x squared term was missing. And so I'm going to divide synthetically by 2, and my coefficients would be 3, negative 6, 0, negative 5, and 10. Those placeholders are really easy to overlook, but nothing works if you don't put those placeholders in there. All right, and so we divide synthetically here. And so remember how we're going to do this. We bring this 3, whatever this first number is, we bring it below the line. And then we start multiplying, and then we write in the next column, and then we add, right? And then we just use that process over and over again until we finish the chart. So 2 times 3 is 6. We write it in the next column. We add, we get 0. We multiply again, 2 times 0. That's okay, there's no problem with that. 2 times 0 is 0. We write that in the next column. We add, and we get 0. 2 times 0 is 0. We write that in the next column. We add, we get negative 5. 2 times negative 5 is negative 10. We write that in the next column, and we add, and we get 0. All right, so right away, what do we get here at the end? We get 0 is a remainder, is the remainder. And so we know right away what the answer to the question is. Yes, x minus 2 is a factor. No question about it. It is a factor. All right, now what is the factorization? That would be the next question. So our polynomial, 3x to the 4th minus 6x cubed minus 5x plus 10, does factor so that x minus 2 is a factor. The other factor is given by the coefficients at the bottom of our synthetic division. And because our original polynomial was degree 4, then the new polynomial, this after we've divided synthetically, has got to be degree 1 less than that. So this has got to be a degree 3 polynomial. And so the 3 represents the degree of the cubed term. The 0 represents the squared term. The next 0 represents the linear term, and then minus 5, like that. So that's, this is the 3 right here. This is that 0. This is that 0. And then this is the constant right here. Now, usually you don't write those terms with the 0 coefficient. So when you factor it, so you usually just write it as x minus 2 times 3x cubed minus 5, like that. And that would be our factorization. Okay. So the next problem I want to look at. So and this is going to be our last problem for the day here. So let's show that x plus 2 is a factor of x cubed minus 6x squared minus x plus 30, like that. So in this problem, what's we're going to use division to do this. And since it says show it's a factor, that means it's implying that it is a factor, and we better get 0 as a remainder. So this is the division we're doing, is we're dividing by x plus 2. Now remember, when I wrote down synthetic division a few minutes ago, when we first started using this, we talked about taking a polynomial and dividing it by something in the form x minus k. So since this is x plus 2, you have to write it as subtraction. So technically, this is x minus negative 2. And so k in this problem is negative 2. And the way most students just remember this is that they just say that the k value is always the opposite sign of whatever's sitting in the denominator there. So synthetically, I'm dividing by negative 2. I write the coefficients down. None of them are, no terms are missing. They're all there. The degree goes 3, 2, 1, 0. So I don't have any placeholders in this problem. So now then I go through my synthetic division. I bring the 1 down. I multiply. Negative 2 times 1 is negative 2. I add. I get negative 8. Negative 2 times negative 8 is positive 16. I write that in the next column. I add, I get 15. Negative 2 times 15 is negative 30. I add, and I sure enough get 0. So since that's a 0 right there, yes, x plus 2 is a factor. And then the factorization looks like this. This is my original polynomial. And then x plus 2 is a factor. And then my other factor, I started with a degree 3 polynomial, so the other factor has to be a degree 2 polynomial. And here are the coefficients for that other polynomial right here. And so this would be 1x squared minus 8x plus 15, like that. And so then notice, by the way, in this one, I can completely factor this one now, because x squared minus 8x plus 15 is also factorable. And I have x minus 3 times x minus 5, like that. And so I could actually completely factor this polynomial once I got that first 0 straightened out and did the synthetic division. So notice the zeros, you could actually write down all the zeros for this function. You get -2, which is the one we were given, but then we also get 3 and 5 as zeros as well. So we actually could find all the zeros for this function based on that first one. All right, now where we're headed here is, notice in this case it said show that x plus 2 is a factor. So you were kind of given that x plus 2 is a factor at the beginning of the problem. So kind of where we're headed on Wednesday is what happens if you're not given a place to start. Where do you start? And we're going to use graphing technology to do that, and then also combine it with these things that we've been talking about with factors and zeros and multiplicities and all that, up kind of trying to put it all together and piece it all together. So that's where we will be headed on Wednesday of this week in Wednesday's lecture. So the homework from the textbook for practice, textbook practice, and maybe that's the way I should call it from now on, is textbook practice. This is section 5.4. This is page 400 in your book. This is practice using synthetic division. And so I would say 15, 21, 21, 29, 35, and then 39 and 41. Like that. And then finally 45 and 47. Those would be good practice on 5.4. And then in section 5.3, which is where we started today, these problems are on page 390. Really, I would like, practice problems, anything from problem 7 through 55 would be good practice. So at the very least, if you'd worked on 7 through 55 every other odd, that would be good practice for what we've been talking about. Very good practice, in fact. Those would be good practice problems for the next exam as well. Okay, so covered a lot of material today. Look forward to your exam grades coming out for exam 1 tomorrow. So I'll be looking for an email from me tomorrow for that. Does anybody have, for those of you who are with me live, are there any questions from any of you guys?
I'm good right now.
I'm good too.
Okay, so everybody's okay. What you guys will find is if you practice this, my experience has been, I've taught this a lot of times over the years. My experience is students who practice this stuff get pretty good at it. Even though it looks a little bit confusing at the beginning, students usually do very well on this material on exams. That is definitely not uncommon. So if you do some practicing and keep up with this, kind of fit all these pieces of this puzzle together, then you'll get the hang of it as you go through the next week, and you'll get pretty good at this also. And so take advantage of that to do a good job on exam 2, definitely, because this will be a big part of exam 2. All right, so all of you guys who are with me live and those of you who are watching later, have a great day, and be looking forward to an email from me about exam 1's grades over the next 24 to 48 hours. So have a good one.